So polymer chains have a lot of conformational entropy. If we put them on the surface of colloidal particles, they can stabilize the colloid as we saw earlier, but let's quantify that. How big is this effect of stabilization of colloids? How much do the particles repel each other because of this entropic repulsion? The equations we use will depend on whether we're in a high grafting or low grafting density regimes. We look at this equation. Pi is given in terms of pressure, is the force per unit area for two approaching surfaces. And we can see that it's going to be proportional to kT, the thermal energy, and that's because this is an entropic effect. We also see that these are, h is the distance between the two approaching surfaces, and L naught is the brush height, since we're working at high grafting density. So we can see these are both in units of meters, so all of this is unitless. Since this is joules, we have joules per meter cubed, and that will give us units of pascals or pressure. Okay, so how many newtons per square meter of area. Great. So this will give us the force of repelling two particles. By the way, we can see that depending upon the distance, this force could be negative. We could have an attraction. So when the two, if we look at this, when h is big compared to L naught, this term is going to get very small, and we're going to end up with an attractive term. And that makes sense, because if we think about it when we're very far apart, we've got our two surfaces, we've got our brushes. Their conformational entropy is not affected by the other surface because we're not there yet. So all this does is essentially bring the particles closer together, and that's going to make them more attractive. Let's look at the low grafting density. For the low grafting situation, we have this equation, and we can see that in this case, the size parameter, of course, is going to be the radius of gyration. Once again, it's an entropic effect, and we have to rewrite the distance between the two particles.